Hello, ladies and gentlemen. My name is Hervé Pruvost, and I am a research engineer at Fraunhofer IIS, Division Engineering of Adaptive System in Dresden, Germany. And on behalf of my colleagues, I would like to present you our work about a recommendation system for energy saving and user engagement in existing buildings. This work has been performed in the context of an European project called eTEACHER, which mission is to engage building users in saving energy and make them better understand their energy usage as well as energy waste by the means of ICT solutions which are connected to the building technical systems. And we applied this solution to into 12 buildings across Europe with the aim in the short term to expand the solution to at a larger scale to more buildings, then contributing in decreasing worldwide energy use and related environmental impact. eTEACHER has involved 12 entities from 6 different countries, including industries, small and medium-sized enterprises, non-profit enterprises, public bodies, one research institute and one university. And it has been coordinated by CEMOSA, which is an engineering company situated in Spain, in Malaga. The eTEACHER goal or concept is to provide a framework of ICT components which are on one side connected to existing buildings, collecting information and data from these buildings, and on the other side, providing end users with tailored advices about their energy usages, and how they can save energy, and also collecting feedback from them. Our work focuses on the recommendation system, which is based on the so-called BACS add-on named What If Analysis, as shown in this concept picture. And the What If Analysis consists of an analytics framework that processes data as well as metadata about buildings and about to provide end users with real-time recommendations about how they can save energy and provide them some propositions of actions to save energy, and also providing estimations of their energy saving potentials if they follow these recommendations. For developing the recommendation system, we faced some constraints. So this is a software tool that analyzes building data in real time for providing energy conservation measures without compromising comfort and environmental indoor conditions for the users. And that's why the availability of data is crucial. It uses building data. It has also, it should be also continuously available because it is used in real time, and also the computational effort of the software and the algorithm behind the recommendation system has to be kept limited. And one major constraint is its flexibility. It means this ability to be applied to any kind of building, regardless of their size, type, and usage, and without having to reprogram or reconfigure manually the tool if we want to apply it to another building. So for tackling the data aspect, so we defined and implemented a monitoring system which consists of a minimal set of sensors and meters which are useful or which are necessary for using the recommendation system. So this monitoring system consists of meters collecting consumptions, energy consumptions for lighting, for appliances, for heating and cooling, also weather data, data about the indoor conditions inside the room and the building, temperatures, humidity, smart sockets, also windows and doors opening contact, windows and door contacts, sorry, as well as occupancy or presence sensors. And where possible, we try to reuse potential existing data from an existing BACS or monitoring system in the building. But as most buildings, existing buildings lack an advanced BACS or monitoring system, we had to install these sensors, relying then on existing technologies from the market, which are usually used in the smart home or smart buildings field, favorizing then rather wireless technologies, which are easier to install and easier to maintain. Another work we performed prior to developing the recommendation system is to go to the buildings, inside the buildings, analyze the current energy usage, consumptions, and also the current behavior of people, how they consume energy and how they waste energy, for then identifying target behaviors, or avoiding bad energy habits, ranging from very simple ones like avoiding leaving lights on when no one is there, or avoiding overheating, undercooling, wasting energy through openings, or also better matching the use of heating and cooling systems with the occupancy of the building. From that, we developed a knowledge base of energy conservation measures, which are divided in different categories according to the type of energy that can be saved. And these energy conservation measures can be applied at different levels, room level, zone or building level, and they were formalized inside the knowledge base in computer readable form by the recommendation system or its software environment, and can then apply them to a specific building under study. For then feeding the recommendation system with real data and provide its results to end users, so we implemented this workflow, which consists of two main interfaces, one with the installed monitoring system. It relies on some industry standards like OPC-UA, which is a standard from the automation field, and also SQL. In that context, we developed a database system, including a database schema for describing the building, metadata about the building, containing its topology, as well as describing its sensor system, and a second interface, which consists of a web interface with a server of the end user applications. One application which consists of a mobile application which can be installed on iOS or Android devices. Now, going deeper inside the recommendation system, so it has been developed as an expert system, which by definition consists of three main components: a fact base, which contains data or information about the problem to solve, a knowledge base. So here the knowledge base of energy conservation measures, which are defined as a set of rules for checking, for analyzing metadata about the building from the monitoring system as well as measurements data. And a third module, which is the inference module, which consists of the algorithmic part of the tool, which then take as input the fact base and the knowledge base to then assess, identify energy conservation measures. So the prototype of recommendation system has been developed using different technologies. It is mainly a Python framework, and also involve different other standards like SQL for storing the time series data, and RDF for describing the metadata about the building, its topology and its energy system. And for the inference module, we define three different layers of inferencing, which are then executed at runtime in a sequential manner, starting from a system characterization step, which is which enables the system to identify the topology of the building, the spaces, the kind of sensors installed, the meters installed, as a type of energy system. A second level, which consists of analyzing the data, the sensor, the measurements data, to then identify energy waste or to assess energy conservation measures. And a third level, which consists of procedural rules, which purpose is to generate the recommendations and allocate, attach them to specific locations, space in the building where they apply. Then all the results are delivered as recommendations over a web interface to the front-end user application. Here, the screenshot of this front-end user application from a mobile app, from a mobile device. The recommendation system then sends continuously, when it applies, recommendations when it detects energy waste or potential energy conservation measures. And these recommendations are delivered over time to the end users, who can then have a look at them and apply them. Then advising him to change temperature set points, to avoid to close open windows, blinds for optimizing solar gain, and so on. And to each recommendation, the tool provides as well as an estimation of the energy saving potential and the target energy saving if the end user then apply this recommendation over a longer period of time. We have then developed the recommendation system, a prototype, and then applied inside the 12 buildings. And for that, we have then asked a pool of persons, different persons, building users, to install the app and use it over several months. And after that, after this period, so we have analyzed the results and made an evaluation of the project, and identify that people using the app could save then up to 50% of energy without impacting on the comfort or compromising the indoor environment of the building. And also we noticed that people used or applied not all recommendation equally, but for example, the temperature set point, changing temperature set points was the one that was the most applied by users. We also noticed that most of the people used the app, which was not obvious because in mobile app, difficulty is to keep people motivated and focused on using it, but the app was also part of the project, integrate a gamification component, and was developed in a user-friendly manner so that people can stick to it and continue applying the recommendations. As a conclusion, so we developed this recommendation system relying on different technologies. It is split in two main parts: metadata processing using semantic web techniques, as well as data processing, time series analysis. It provides the end users with real-time energy conservation measures, and it is a rule-based expert system. And we can say it is also a model-based expert system, which brings its flexibility because, or thanks to the metadata processing that enable it to process information from a building description, building topology, to then configure different checking rules and data processing rules to then identify energy conservation measures. It is run as a cloud service at Fraunhofer premise, and it makes it quite easy to install and easy to deploy as soon as the both required interface are available, an interface to the monitoring system and the interface with the end user app. By analogy, in contrast to a modern back system, we can say that it applies an indirect control, meaning that it does not send signals or try to control an actuator system, but send recommendations to people, which are then themselves engaged in performing actions and towards energy saving. And we are working on further extensions for the recommendation system, integrating it with BIM, so building information modeling, because BIM provides a lot of metadata, a full description, even very detailed description of the building, and that would be a means of completely automating the workflow of the recommendation system. If it takes as input BIM, then it can detect automatically the topology of a building, and even with a digital twin, it could even assess and interpret a complete building and monitoring system. Also, we want to extend the knowledge base to more use cases, for example, for facility managers, for detection and diagnosis, and also integrate further AI methods from machine learning to then enhance the functionalities or extend the functionalities of the tool, and also couple it with simulation for better or more detailed energy saving estimations. So this was all about this this system and this project. I hope you enjoyed it and you are interested in further following this. You can follow our project and our results of the canals which are indicated on this slide, and don't hesitate to visit our website to get informed about next steps. And if you want to try it, then we will, in the short term, try to deploy it to a larger, broader audience.